Imagine you have a license plate and a list of words. Your goal is to find the shortest word that contains every single letter from that plate. How would you solve this? Take a moment and think. Let's break down exactly what this problem is asking. We are given two things: a license plate, which is a string that can contain numbers, spaces, and letters, and a list of words. We need to find the shortest word in that list that is a completing word. Now, what does completing word actually mean? It means the word must contain every letter that appears in the license plate. If the license plate has two S's and one T, the word must have at least two S's and at least one T. It doesn't matter if the word has extra letters. It just needs to cover the requirements. Let's look at an example. Suppose the license plate is 1S3PST first. We ignore the numbers and spaces. So our requirements are S, P, S, and T. That's two S's, one P, and one T. Now look at our list of words. The word step has S, T, E, P. It has one S, one T, and one P, but we need two S's. So step is not a completing word. Next is steps. It has S, T, E, P, S. That's two S's, one T, and one P. This works. Now we check stripe. It has S, T, R, I, P, E. Only one S, not a completing word. Finally, steple has S, T, E, P, P, L, E. Only one S, not a completing word. The only valid word was steps, so that's our answer. What makes this tricky is that we aren't just checking if a letter exists, but if it exists enough times. If the plate has three A's, the word must have at least three A's. Also, we have to handle case sensitivity, meaning a capital P is the same as a lowercase p. We are looking for the shortest one. So if multiple words work, we pick the one with the fewest characters. If there is a tie in length, we pick the one that appeared first in the list. This means we have to be very careful about how we track our requirements and how we compare the words. The most obvious thing to try is a direct search. We would take the license plate, clean it up by making everything lowercase, and then for every single letter in that plate we check if it's a letter. If it is, we go through every word in our list. For each word we check if it contains that specific letter. But wait, if we just check if the word contains the letter, we might miss the count. So for every letter in the plate we would have to search the word, find the letter, and then somehow mark that letter as used so we don't count the same letter twice. Let's trace this with our example. Plate is 1S3PST. We see the first S, we check the word step. It has an S, great. Then we see the P step has a P, great. Then we see the second S step has another S. No, it only has one. So step fails. We move to the word steps, first S. Yes, P. Yes, second S. Yes, T. Yes, steps works. But we can't stop there because we need the shortest word. We have to check stripe and steple too. This approach is slow because for every single letter in the license plate, we are scanning through every word, and inside that we are scanning through every character of the word. In technical terms, if N is the number of words, M is the average length of a word, and K is the length of the plate, our time complexity is O of N times M times K. This is because we have three nested layers of searching. We are repeating the same work over and over, scanning the same words multiple times for different letters. This is inefficient because we are treating each letter as a separate search, instead of looking at the word as a whole. The key insight here is to stop searching for letters one by one and instead create a frequency map of the requirements. Think of it like a shopping list. Instead of going to the store and looking for milk, then coming home, then going back for eggs, you write down exactly how many of each item you need and check them off in one trip. We can use an array of 26 integers to represent the alphabet. Each index corresponds to a letter from 0 to 25 for Z. First, we create a requirement array. We loop through the license plate, and for every letter we find, we increment the count at that letter's index. Now we have a perfect map of exactly how many of each letter we need. Next, we keep track of the shortest completing word found so far, starting with nothing. We then loop through each word in the list. For each word, we create a second frequency map. We count every letter in the current word. Once we have the word's map, we compare it to our requirement map. We loop from 0 to 25. If the requirement map has a higher number for any letter than the word map does, it means the word is missing some letters. We mark it as invalid and move to the next word. If the word is valid, we check its length. If it's shorter than our current best, or if we haven't found any word yet, we update our best word. By using these maps, we only scan the license plate once and each word once. We've replaced the repeated searching with a simple comparison of two arrays of size 26. This is much faster because comparing two small arrays is a constant time operation, regardless of how long the words are. Let's trace this optimal approach with our example. Plate is 1s3pst. We create our requirement array of 26 zeros. We see 1, ignore it. We cease, so index 18 becomes 1. We see 3, ignore it. We see p, so index 15 becomes 1. We see s, so index 18 becomes 2. We see t, so index 19 becomes 1. Our requirement map is now: index 15 is 1, index 18 is 2, index 19 is 1, all others are 0. Now we look at the first word step. We create a word map of 26 zeros. We cease, index 18 becomes 1. T, index 19 becomes 1. E, index 4 becomes 1. P, index 15 becomes 1. Now we compare. Index 15, requirement 1, word 1. OK. Index 18, requirement 2, word 1. Stop. 2 is greater than 1. This word is invalid. Current shortest is still null. Next word steps. Word map. Index 18 becomes 1, T index 19 becomes 1, E index 4 becomes 1, P index 15 becomes 1, index 18 becomes 2. Now compare. Index 15, requirement 1, word 1. OK. Index 18, requirement 2, word 2. OK. Index 19, requirement 1, word 1. OK. All other requirements are 0, so they are all OK. This word is valid. Current shortest becomes steps. Next word stripe. Word map. Index 18 is 1, T index 19 is 1, R index 17 is 1, I index 8 is 1, P index 15 is 1, E index 4 is 1. Compare. Index 18, requirement 2, word 1. Stop. 2 is greater than 1. Invalid. Current shortest is still steps. Next word steple. Word map. Index 18 is 1, T index 19 is 1, E index 4 is 1, P index 15 is 1, P index 15 is 2, L index 11 is 1, E index 4 is 2. Compare. Index 18, requirement 2, word 1. Stop. 2 is greater than 1. Invalid. Current shortest remains steps. We have finished the list. The final answer is steps. You'll spot this pattern whenever a problem asks you to check if one string contains all the characters of another, including duplicates. Whenever you see requirements based on character counts, think of a frequency map or a fixed size array of 26. The time complexity is O of n times m, where n is the number of words and m is the average word length. Space complexity is O of 1 because our arrays are always size 26. Try the valid anagram problem next. It uses the exact same frequency map pattern. Subscribe for more DSA breakdowns.